So friends, in the previous video lecture, we have discussed about the sign convention of the shear force and the bending moment diagram. And today we are going to discuss a numerical problem based on those sign conventions. And earlier we have also solved certain problems also based on these sign conventions. So the link of the sign convention video is pasted in the description box. Okay, so you can see these sign convention from there for more information. Now, let us start this problem. This is a cantilever beam which is subjected to a point load at this point B and a concentrated movement at this point C. Okay. Now friends, this is the length L, this is L and this is L. Between C and D, between B and C and A and B are L. Now we have to draw the shear force and the bending moment diagram for this problem. So the first thing is that we have to find out the net reaction which is acting at this point A. So the net vertical load F net vertical load which is acting at this point A, the net vertical load which is acting at this on this cantilever beam is how much? 2W. 2W load is acting on this cantilever beam. So this load is acting in vertically downward direction. So the reaction in vertical direction at the point A will be equal to this net vertical load and will act in a direction which is opposite to this net vertical load. So it will be 2W and will act in direction opposite to this F net. Okay. Now the reaction movement we have to find out at this point A. For that we have to find out the net movement acting at this point A. At this point A we have to find out the net movement for that. So the net movement acting over the point A will be because of this load and because of this concentrated movement. So because of this load there will be a movement in clockwise direction about the point A. So it will give us 2W, the magnitude, into this distance L in clockwise direction. And because of this concentrated movement there will be a movement at this point A in anti-clockwise direction and it will have a magnitude WL in anti-clockwise direction. Okay, why? Because this is going in anti-clockwise direction with respect to point A. Now the net reaction movement at point A we have to find out, then it will be equal to this net movement. So the net movement at the point A, the net movement at this point A is equal to WL in clockwise direction. Why? Because this WL, 2WL will cancel out with WL to give only WL in clockwise direction. Okay, so the reaction movement at point A we have to find out, it will be equal to the M net, that is the net movement acting at the point A, and its direction will be opposite to that of net movement, so it will go into anti-clockwise direction. So we will show here the reaction at A in vertical direction with this sign, and the net movement acting at this point A will be shown by this red color. Okay, and it is acting about this point A and it is MRA. Okay, and it is going in anti-clockwise direction. That is this direction it is going. Okay, now friends, we have to draw the shear force and the bending moment diagram. First we will determine the shear force. So shear force calculation will begin from here. Okay, now we will start from point A and go to point D. So shear force we will calculate first at point A. Shear force at point A we will calculate. Okay, now because a concentrated load is acting at this point A, that's why shear force will change from left side of the point A to the right side of the point A. So we have to calculate the shear force on the left side of the point A and on the right side of the point A separately. Okay, now let us take the shear force on the left side of the point A. So for that we have to draw a section on the left side of this point A. Suppose this is the section drawn on the left side of this point A. Okay, now we know that according to the definition of the shear force, that shear force at any section is the summation of all the forces either on the left of the section or on the right of the section. So we will take the left of the section. Okay, you can take right of the section also, but here for simplicity I am taking the left of the section. So on the left of this section there is no load acting. Okay, that's why the shear force on the left of the section is 0. And on the right of the section, if we want to calculate the shear force right of the point A, if we want to calculate the shear force on the right of the point A, then what we have to do? Then we have to construct a section on the right side of this point A. Okay, so this is the section I am constructing on the right side of the point A. This is the section XX. Now on the left side of this section, you can see that there is a force RAB acting at the point A. So it will constitute toward a positive shear force of RAB, magnitude RAB, and RAB is equal to 2W. So it will give us 2W positive shear force. Positive why? Because this force RAB, see here, this force RAB, suppose is acting at point A, this RAB here, okay, and this is our section XX, okay, this section XX is here, okay, I am generating this part of the portion of the beam here, and we can see that this direction RAB is trying to rotate the beam element between the point A and this point, which is lying on this section XX, in clockwise direction with respect to this point. Okay, this force is trying to rotate this beam element in clockwise direction with respect to this point. That's why it is taken as positive shear force. Okay, so it will give us positive shear force. Now we will calculate the shear force, okay, at point B. In the left side of the point B we will calculate, and in the right side of the point B we will calculate the shear force. Why? Because there is a point load of 2W is acting at point B, and due to which the shear force will change as going from the left side of the point B to the right side of the point B. Okay, so that's why we will find the shear force on the left and on the right side of this point B. So to calculate the shear force on the left side of the point B, first we have to rub this previous section taken here and take this section here on the left side of this point B. So on the left side of this point B I am taking this section XX, and according to our sign convention, the shear force, because of this force will only account because of this load, there will be a shear force at this section XX, and this force will account for a positive shear force, because the concentrated movement will not account for any shear force about this section XX. Okay, so this RAB will give a shear force of, which is this RAB is equal to how much? 2W. Give us a shear force of plus 2W. Why plus W? Similar condition, because here sign convention is taken as positive clockwise rotation. So plus W will be there, and it will only account for 2W shear force about this section XX because of this reaction RAB. Now going on the right side of this section B, to calculate the shear force on the right side of the section, the right side of the point B, we have to redraw this section here. Okay, so we will draw a section here on the right side of this point B. Okay, now look at the various forces which are acting on the left side of this section. So this force is acting on the left side of the section, and this force is acting on the left side of this section. So these two forces will account for shear force about this section XX, and this concentrated movement will not account for any shear force about this section XX. Okay, so because of this force there will be a shear force of plus 2W, and because of this concentrated load there will be a shear force of minus 2W. Why? Because this will cause a rotation of the beam element which is lying between the point B and this point which is lying on the section XX in the anti-clockwise direction. How? Let us see this. Suppose this is the section, this is our section XX. I am drawing the previous section from here, okay, and this is our section XX, and this is the point B, suppose, okay, and there is a force which is acting in the downward direction, okay, like this. So this force is trying to rotate this beam element in counterclockwise direction, so it will be taken as negative. Okay, so that's why we have taken it here as negative, and it will give us how much? 0. Now we will calculate the shear force at the point C, because there is no point load acting at, so it will be taken as negative. Okay, so that's why we have taken it here as negative, and it will give us how much? 0. Now we will calculate the shear force at the point C, because there is no point load acting at the point C. That's why we will directly calculate the shear force at the point C. We will not calculate on the left side and on the right side of the point C. So constructing a section, first we will erase this section and construct a section which is passing through this point C. Now see this. On the left side of this section there are two forces, this one and this one. This will account for positive shear force, this will account for negative shear force. So this one will give 2W plus 2W, and this will give minus 2W about this section XX. Again it will come out to be 0. Now shear force at section D, because at section D there is no force lying, there is no concentrated load lying. That's why shear force at section B can be found out by directly constructing the section at the point D. Okay. Now looking on the left side of this section, you can see that there is only two forces lying. That's why these two forces only account for shear force about this section XX, and the concentrated movements will not account for any shear force about this section XX. Okay, so because of this RAV, there will be a shear force of plus 2W about this section XX, and because of this 2W, there will be a negative shear force of magnitude minus 2W. So it will again give us 0. Now we will construct the shear force diagram. Okay, so let us generate these point, that is, we will project these point A, B, C at which the loading is there, and this D point here, and join these point with a line, and we can see that this is the point A, this is the B, this is the C, and this is the D. Now see friends, at the point A the shear force is 0. See, so we will mark here the 0 point here, and one thing we have to remember, that above this line shear force is treated as positive, and below this line shear force is treated as negative. So on the right side of the point A, the shear force is plus W, so it is increasing to plus 2W. Okay, plus 2W. This distance is 2W. Okay, and on the left side of the point B, you can see that it is 2W. So 2W will lie in the same level here above the point B. Okay, and it's again going to 0 in the right side of the point B. Okay, right side of the point. And in the shear force at the point C is 0 again. So mark 0 here, and shear force at D is 0. Okay. So we will join these points. First point will be joined with second, and second will be joined with third with a straight line. Why we are joining these 2 points with a straight line? Because between the point A and B there is no loading acting, and we will join the third with the fourth, and fourth is joined with the fifth, and fifth with the sixth. So we will get the shear force diagram here. Okay. Now we will draw the bending moment diagram. For that we have to calculate the bending moment at the various points. Okay. So I am rubbing this. Now in the bending moment calculation, okay, what we have to do? Now we will calculate the bending moment. Okay. So for bending moment, we have to start with the point A. So bending moment at point A, we will calculate. We will calculate the bending moment on the left side of the point A, and bending moment on the right side of the point A. Why? Because there is a concentrated movement acting at this point A. So bending moment will change suddenly as going from the left side of the point A to the right side of the point A. So for calculating the bending moment on the left side of the point A, we have to construct a section on the left side of this point A. Suppose this is the section which is being constructed on the left side of this point A. Now according to the definition of the bending moment at a section, we know that bending moment at a section is the sum of all the movements either taken from the left side of that section or on the right side of that section. So we will take the left side of this section in our discussion. So on the left side of this section, there is no bending moment acting. Okay, so there is no force lying actually, and there is no concentrated movement. So that's why bending moment about this section will be 0 on the left side. And on the right side of the point A, if we want to determine the bending moment, then we have to construct a section on the right side of the point A. So this is a section. So looking at the left side of this section, there is a concentrated movement which is having a magnitude of WL. This WL is acting here, and there is a force also lying on the left side of this section. So this movement will contribute towards the bending movement at this section XX. but this force will not contribute toward the bending moment at this section XX, because the distance between the point A and this section XX, okay, is negligible. Okay, it is very close to point A, but for clarity I have shown here with at a distance from the A, this section. So actually this section is very close to point A, that's why this distance is negligible, and the movement due to this force RAB about this section is 0. That's why we will take only this concentrated movement we will consider only this concentrated movement. So bending moment at this section XX will be equal to how much? It will give us minus the magnitude of this movement I am writing here. This is actually M RA, and it is equal to how much? WL. Okay, so it will give us minus WL. Okay, why it is minus WL? Negative sign is coming. See the sign convention. For the concentrated movement, the sign convention is as follows. I have explained in detail the sign convention in the video, the link of which is pasted in the description box. See this section XX. If this is our section XX, similar to this section XX, and if the movement is acting on the left side of that section, that section, then it can be treated as positive if it is going in anti-clockwise direction, and it can be treated as negative if it is going in anti-clockwise direction. So this is our section XX, and similarly this is our section XX according to sign convention, and this movement is going in left side of this section XX and this movement is also going in the left side of this section XX, and it is going in anti-clockwise direction. Okay, and this movement is also going in anti-clockwise direction, so will be treated as negative, so it will also be treated as negative. That's why negative sign appear here. So we will use the similar sign convention for positive movement, this sign convention, and negative movement, this sign convention, for all the movements which are lying on the LHS of this section XX. Okay, now bending moment, okay, at the point B we will calculate. We will not calculate the bending moment on the left side and on the right side of this point B. Why? Because there is no concentrated movement is acting at this point B. That's why the bending moment will not change suddenly when going from the left side of the point B to the right side of the point B. Okay, so bending moment at B we will calculate directly by constructing a section at this point B. Suppose this is the section XX being constructed here at the point B. So on the left side of this section you can see that there is this force, there is this load acting here at the point A, and the concentrated movement is acting at this point A. Now because of this force there will be a bending moment at this section XX, which will be given by 2W, that is the magnitude of that force, this 2W into this distance L, and it will create a sagging bending moment. Okay, because sagging is treated as positive. This is sagging, it will treat it as positive. Why? I am showing 2, and we will follow that sign convention in the later part of this problem. Okay, if this was our point B, suppose, and the section XX was passing from here, okay, and this is the point A, okay, of the beam, suppose, and this was our reaction RAV. Now this RAV is trying to rotate this beam element, okay, in this direction, means upward direction. So it will create a bending like this of this beam element AB. Suppose this is A, this will be A dash, and it will create a concavity up like this. Okay, that's why it is treated as positive. So the bending moment at B because of this force will be positive when it will have a magnitude 2W into L, and because of this concentrated movement, this bending moment will be minus WL, using this sign convention, similar sign convention for the concentrated movement. Okay, now bending moment at C we will calculate on the left side of the point C and on the right side of the point C the bending moment. Why? Because the bending moment will change suddenly when going from point on the right side of the point C to the from the left side of the point C to the right side of the point C, because there is a concentrated movement acting over here, okay, at WL at point C. So bending moment on the left side of the point C, okay, so we will calculate. For that we have to construct a section on the left side of the point C. Suppose this is the section being constructed on the left side of this point C. Okay, this is the section XX. Now on the left side of this section, because of this force, there will be a bending moment of plus 2W, okay, plus 2WL plus 2W into 2L, that is this force magnitude into this distance between A and C. Okay, and because of this force there will be a movement of minus 2W into this distance between B and C, which is L. It is hogging, it is creating a hogging bending movement about this section, which is passing through this, about this section XX. Okay, now because of this concentrated movement there will be a negative bending movement of minus WL. Okay, so it will give us bending moment as 2WL, 4WL and 2WL, and it will give us a bending moment of how much? WL. Okay, now bending moment at the point on the right side of the point C, if we want to calculate, then we have to again construct a section on the right side of this point C and look for the various forces that are acting on the left side of this section. So because of this movement there, because of this force, there will be a movement of plus 2W into 2L sagging. Okay, and because of this force there will be a movement of this force, there will be a movement of 2W into L hogging, and because of this force there will be, because of this movement there will be a movement of concentrated movement, there will be a movement of minus WL according to the sign convention, and because of this force this is going in clockwise anti-clockwise direction also, so because of this there will also be a movement of minus WL because of this concentrated movement. Okay, so it will give us again 0. Now we will calculate the bending moment at point D. So at the point D we will directly calculate the bending moment because there is no concentrated movement at this point D. So I am rubbing this section and constructing a section at point D. Now looking for the various forces on the left side of this section and the movement. So bending moment because of this reaction RAV will be equal to 2W into this distance 3L. Because of this force there will be bending moment of minus 2W into 2L. This is sagging and this is hogging, and because of this concentrated movement there will be a movement of minus WL, and because of this also there will be a bending moment of minus WL about this section XX. Okay, so it will again give us 2 3 are 6 and 2 2 are 4 5 6, that is 0. Okay, so we will draw the bending moment diagram now. So the bending moment diagram will look like this. This is the point D, this is the point C, this is the point B, and this is the point A. Now bending moment at point A is 0. Bending moment on the right side of the A is minus WL, so going negative direction downward, minus WL. Bending moment at B is equal to how much? It will come out to be WL. Okay, that is going in at this point WL, and this is WL, and bending moment at point C on the left side is WL. It's WL here over the point C, and bending moment at the right side of the point C is 0. So here it is 0, and bending moment at D is 0. So joining this point, first point with the second, and second point is joined with the third point with the inclined line. Why? Because between the point A and B, the shape of shear force diagram is a straight line. So the shape of what bending moment diagram will be a inclined line between the point A and C, and we will join the third point. So we will join this point B with this point C, that is the third point with the fourth point, and fourth point with the fifth point, and fifth point with the this sixth point. Okay, so we will get the bending moment diagram. This is negative and this is the positive. So this is the all for today's topic, friend. If you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming video.